Hello everyone, this is lecture 18, maxima and minima problems. In single variable calculus, we show how to use derivatives to find maximum and minimum values of functions of single variable. When those techniques are extended to functions of two variables, we discover both similarities and differences. So the landscape of a surface is far more complicated than the profile of a curve in the plane. So we see more interesting features when working with several variables. In addition to peaks, which is maximum values, and hollows, minimum values, we encounter windy ridges, long valleys, and mountain passes. Yet despite these complications, many of the ideas used for single variable functions reappear in higher dimensions. For example, the second derivative test adapted for two variables plays a central role. As with single variable functions, the techniques developed here are useful for solving practical optimization problems. And that is the motivations for this lecture. And hopefully after this lecture, you could be able to use partial derivatives to locate critical points for functions of two variables. You could be able to apply a second derivative test to identify a critical point as a local maximum, local minimum, or a saddle point for a function of two variables. So the difference between single variable functions and a function of two variables is a new concept of saddle points. And you could be able to examine critical points and boundary points to find the absolute maximum and absolute minimum values for a function of two variables. Now, for definitions of maximum and minimum for a function of two variables, a function f of x, y has a local max at the point x0, y0 if f of x, y is greater than or equal to f of x0, y0, and a local minimum at x0, y0 if f of x, y is less than or equal to f of x0, y0. And f of x0, y0 is called a local max or min value, or you can call it a local extreme value. So let's take a look at the following image. So it depends on the regions of considerations that you may have a different terminology for a point of considerations. It might be local or global maximum, local and or global minimum. For instance, if you consider this point on the entire domain of the functions, then this point represents a global maximum. If you examine this point on an open region, then this point represents a global maximum. Similarly, if you consider this point on the entire domain, there's no conclusion on the global value. If you examine this peak on an open region, then you can conclude that this peak represents a local maximum and not a global maximum. On the other hand, if you examine this point on the entire domain, this point represents a global minimum. But if you examine this point on an open region, this point represents a local minimum. If you consider the graph of the paraboloid, this point 1, 3, 4 is a global minimum if you consider this point on the entire domain of the functions. On the other hand, if you examine this point on an open region about 1, 3, 4, then the point 1, 3, 4 represents a local minimum. So you can note here this is the local minimum. So you can conclude here that 1, 3, 4 is a local minimum on an open region. And 1, 3, 4 is a global minimum on the entire domain of the function f. Now let's move on to a different definition. In this definition, we're going to consider critical points or critical numbers. Let z equal to f of xy be a function of two variables that is defined on an open set containing the point x0, y0. Then the point x0, y0 is called a critical point if one of the following conditions holds. That is, the partial derivative of the function with respect to the x value evaluate at the point x0, y0 equal to 0. And the partial derivative of the function with respect to y evaluate at x0, y0 is also equal to 0. Or either the partial derivative of the function with respect to x or the partial derivative with respect to y does not exist. So these definitions look more or less similar to the one we learned in single variable calculus. That is, to identify the critical point or critical number, you take the first derivative of the function, set that equal to 0, and solve for the value of x, or where the first derivative does not exist. For single variable calculus, this is a function has a local maximum, and local maximum, the function attends a horizontal tangent line, and when we have a horizontal tangent line, that is the first derivative of the function at the point of consideration is equal to 0. Similarly, when you have a function of two variables, you have a tangent plane at the point of considerations, which implies that is the gradient vector of the function has partial f partial x to be equal to 0 and partial f partial y to be equal to 0 at the point of considerations, which match with the first conditions that we have here. Okay, so let's try to find the critical numbers of function of two variables. It depends on the function, but to find the critical numbers, what you do is find the partial derivative of the function with respect to x and find the partial derivative of the function with respect to y, set them equal to 0, and you solve for the value of x and y. And on the other hand, there may be some functions that when you take the first derivative of the function, the first derivative of the function does not exist at a certain point, and that certain point is the critical point. Now for this function, you have the function f of x y equal to x squared plus y squared minus 2x minus 6y plus 14. Then you take the partial derivative of the function with respect to x, and you get 2x minus 2. You set this equal to 0, and you solve for x, and you get x equal to 1. Now for partial derivative of the function with respect to y, you have 2y minus 6, and then you set this equal to 0 and solve for y value. You get y equal to 3. Now combine these two values together, you have a point that is 1, 3, and that is the critical number that you're looking for. Then the critical number is 1, 3. So this is an easy example to demonstrate to you how to find the critical number of function of two variables. Now we're going to move on to second derivative test. The second derivative test will allow you to locate a local minimum or locate a local maximum. And also there's a new concept called the saddle point that may occur in the graph of surface of function of two variables. Alright, so here goes a second derivative test. Let p equal to x0, y0 be a critical point of the function f of xy. Assume that the second order partial derivative with respect to x and second order derivative with respect to y, and the second order mixed partial derivative xy are continuous near p, and the discriminant d is given by d equal to d of x0, y0 equal to the formula fxx evaluate at x0, y0 times fyy evaluate at x0, y0 minus fxy square evaluate at x0, y0. So this is called the discriminant, and we're going to use the discriminant to locate a local minimum or a local maximum as well as the saddle point of the functions. Now if the discriminant is positive and fxx of x0, y0 is positive, then you can conclude that f of x0, y0 is a local minimum. On the other hand, if the discriminant is positive and fxx evaluate at x0, y0 is less than 0, then you have f of x0, y0 is a local maximum. If the discriminant is less than 0, then you can automatically conclude that the function f has a saddle point at x0, y0, comma f of x0, y0. And if d is equal to 0, then the test is inconclusive. You may want to look into a different approach to locate local maximum and local minimum. So the test is inconclusive. And this formula for the discriminant is given to us, but the concept of saddle point is new to us. So by definition, a saddle point is the critical point of the function f of xy that corresponds to neither a local minimum or local maximum of the functions. So in this case, when you see these three different graphs, in the first graph is represent a local maximum. In the second graph, it represents a local minimum. And on the third graph is the point at this point, and this point represents a saddle point. So it's a saddle point because at the point of considerations, you can see the graph of the function to look like a saddle on a horse. Now we're going to use the second derivative test to some example. In example 2, you want to find the critical point of each of the following functions and use the second derivative test to find a local extrema of the functions. F of xy equal to 4x squared plus 9y squared plus 8x minus 36y plus 24. When I say local extrema, that means the local maximum or local minimum. So here's the procedure. The first thing that we need to do is to find the critical point of the functions. So to find critical point, you take the partial derivative of the function with respect to x, set that equal to 0, and solve for the corresponding x and y value. Then you take partial derivative of the functions with respect to y, set that equal to 0, and you find the corresponding x and y value. So for this function, f sub x is equal to 8x plus 8. You set this equal to 0, and you solve for x, you get x equal to -1. Now for the partial derivative of the function with respect to y, you have 18y minus 36. You set this equal to 0 and you solve for y, you get that y is equal to 2. Then the critical point is -1, 2. And eventually we need to use the second derivative test to find local minimum and local maximum. And to get to discriminant, we need the second order partial derivatives. So we're going to do second order partial derivatives. So you need f sub xx. So this is second order partial derivative of the function with respect to x. You get 8. You do fyy, which is the second order partial derivative of the function with respect to y. You have 18. And f sub xy, which is the mixed partial derivative of the function. So in this case, you can either start with f sub x or f sub y. When you start with f sub x, you can take partial derivative function with respect to y. When you start with f sub y, you're going to take partial derivative of function with respect to x, because by Clairaut's theorem, the mixed partial derivative to be equal to one another, so it doesn't matter where you start. So I'm going to start with partial x. We're going to start with f sub x and then take partial derivative of the function with respect to y. We're going to get 0 because there's no y dependent in the first derivative function here. Now we have a second order partial derivative. We're going to substitute this into the discriminant of the second derivative test. So we're going to do second derivative test. And we get that d is equal to fxx times fyy minus fxy squared. For fxx is equal to 8, fyy is equal to 18 minus 0 squared. So this is going to be always a positive number. Again, I'm not going to calculate the exact value. I just want to know the sign of the discriminant. And with this information together with the information of f of xx is always going to be positive, then this implies that the critical point of -1, 2 is a local minimum. So what we just did is we locate a local minimum on the graph of this function. To find a local minimum value or to find a local extreme value, what you do is you substitute x value and y value back to the original functions. So the local minimum value is evaluated as you have f of -1, 2. So x equal to -1 and y equal to 2. You substitute those into the original functions and you get 4 times -1 squared plus 9 times 2 squared plus 8 times -1 minus 36 times 2 plus 24. And if we do the calculations correctly, we're going to get -16. And -16 is a local minimum value, and the local minimum value occur at the point in -1, 2. Now I'm going to move on to another example. In this example, we have a function of the form f of xy equal to x cubed plus y cubed minus 12xy. And you want to find the critical point and use the second derivative test to find the local extrema of the functions. Again, when I say local extrema, I mean local maximum and local minimum. Now for the critical numbers, or the critical points, what you do is you take the first partial derivative of the function with respect to x, set that equal to 0. You do the same thing for the first partial derivative of the function with respect to y, set that equal to 0. Together, we're going to find critical numbers of the functions. So f sub x is equal to 3x squared minus 12y. Set this equal to 0. So obviously it's not as straightforward as the previous example when you can automatically find the value of x and value of y. So in solving this equation, you see that x and y depends on one another. So here you can solve for 12y. This is equal to 3x squared, or y is equal to 1/4 times x squared. Then we move on to partial derivative of the function with respect to y. You have 3y squared minus 12x. Set this equal to 0. And from here, we're going to solve for x value and y value. That is, you're going to substitute y equal to 1/4x squared into this equation. And you get 3 times 1/4x squared all together square minus 12x equal to 0. And you get that is 3 times 1/16 times x to the 4th minus 12x equal to 0. If you multiply 16 for every term in the equations to get rid of the denominator, we're going to get 3 times x to the 4th minus 192x equal to 0. And from here, you can see that 3x is a common factor. You get 3x times x cubed minus 64 equal to 0. And you can solve for x. There are two values of x here. X is equal to 0 and x is equal to 4. So from here, you get x equal to 0 and x equal to 4. So when x is equal to 0, you get y equal to 1/4 times 0 squared. So what I did is I substitute x equal to 0 in this relationship between x and y. On the other hand, when x is equal to 4, you have y is equal to 1/4 times 4 squared, and you get 4 for the answer. So there are two critical numbers. The critical numbers are, or the critical points are 0, 0 and 4, 4. Now next we're going to calculate the second order partial derivatives. You have fxx. We're going to start with the first derivative here and take another partial derivative with respect to x, and we're going to get 6x. Then we do fyy. We're going to use this function right here, 3y squared minus 12x, and we're going to take another partial derivative of the function with respect to y, and we're going to get 6y. Then for the mixed partial derivative, we're going to get negative 12. Then for the second derivative test, we get that d is equal to fxx times fyy minus fxy squared. You're going to have 6x times 6y minus negative 12 squared, or you have 36xy minus 144. Now, it depends on the value of the discriminant and value of fxx evaluated at the critical point. You may have different conclusions on the critical point. So I'm going to make a table here to aid my calculations. So this table includes the following information. That is, for the first column, I'm going to have the critical points. In this case, you have 0, 0 and 4, 4. In the second column, I have calculations of the discriminant evaluated at the critical points. The third column is the evaluations of fxx. And the last column will be the conclusions that we need to draw depend on the value of d and of fxx. So conclusions. Now for the discriminant, you're going to evaluate the discriminant at the critical point, x equal to 0, y equal to 0. And you're going to see 36 times 0 minus 144. You get this to be negative value. And when the discriminant is less than 0, you can automatically conclude that the critical point 0, 0 is a saddle point. Now for the critical point 4, 4, you're going to see 36 times 4 minus 144, and it's going to be a positive value for a discriminant. And for fxx, we're going to do 6 times 4, which is 24, which is a positive number. Then, when you have d is greater than 0 and fxx is greater than 0, you can conclude that at this point 4, 4 is a local minimum. And to find the saddle point value and the local minimum value, what you do is you substitute x and y value back into the original function to find the z value. So here you do f of 0, 0 is equal to 0 cubed plus a 0 cubed here minus 12 times 0 equal to 0. So this is the saddle point value. So when I say center point value or minimum value or maximum value, I'm talking about the output of the function or the z value evaluated at x and y. Now for the local minimum value, you do f of 4, 4. You have 4 cubed plus 4 cubed minus 12 times 4 times another 4, and you get negative 64. And this is a local minimum value. Now we're going to move on to the last example of the selection node. You are given a function of the form f of xy equal to x to the 4 plus y to the 4 minus 4xy plus 1. You are asked to find the critical point of the function and use the second derivative test to find the local extrema of the function. Similar to the last two examples, the first thing that we need to do is to find critical points. So I'm going to take the first partial derivative of the function with respect to x. I'm going to get 4x cubed minus 4y and set this equal to 0. Then I'm going to solve for y in terms of x, and that is y equal to x cubed. Next, I'm going to take the first partial derivative of the function with respect to y, and I'm going to get 4y cubed minus 4x, set this equal to 0, and use the relationship between y and x here to find the corresponding x value and the corresponding y value. So I'm going to substitute y equal to x cubed into this equation, and I'm going to get 4 times x cubed raised to the third power minus 4x equal to 0. Here I'm going to get 4 times x to the power 9 minus 4x equal to 0. And 4x is a common factor. You left with x to the power 8 minus 1. This is equal to 0. When you solve this equation, you have x equal to 0 is one value, and then x to the power 8 equal to 1. You have that x is equal to 0 is one value, or is one solution to the equations. Then you can solve for x to the 8 minus 1 equal to 0, or you do x to the 8 equal to positive 1. When you take the square root on both sides of these equations, you're going to get x to the 4th equal to plus and minus 1, but we're going to eliminate the negative value as we just consider the real value functions. So I'm going to drop a negative 1 and just going to have x to the 4th equal to 1. Then we're going to take another square root, and I have x squared equal to plus and minus 1. Again, I'm going to drop a negative value because I just want to consider the real value functions here. So you have x squared equal to 1. Then take another square root on both sides of the equations, and I'm going to get x equal to plus and minus 1. So there are two values of x here when you consider the solutions of the equation x to the 8 minus 1 equal to 0. So from here, you may conclude that the function has 3 critical points. So when x equal to 0, y is equal to 0 to the third power, or 0, so one critical point at 0, 0. When x equal to positive 1, you have y equal to 1 to the third power. Well, this is equal to 1. You have a second critical point at 1, 1. Then when you have x equal to negative 1, you have y equal to negative 1 to the third power. Well, this is equal to negative 1. Then you have a third critical point, which is negative 1, negative 1. And these are the critical points. Now, following our procedure, the next thing we need to do is to calculate the second order partial derivatives of the function. So second order partial derivatives. So that is, we're going to calculate f(x)(x), and that is going to be equal to 12x squared. f(y)(y), this is going to give us 12y squared. And the mixed partial derivative f(xy) is going to give you negative 4. Now we're going to use the second derivative test to classify the critical number to see if that saddle point, a local minimum or a local maximum, or is going to be inconclusive in our situations here. For the second derivative test, the discriminant is given as f(x)(x) times f(y)(y) minus f(xy) squared. So you get 12x squared times 12y squared minus negative 4 squared. Or you have 144x squared y squared minus 16. Similar to the last example, I'm going to draw a table to aid with my calculations. So for this table, the first column contains critical points. That is 0, 0, 1, 1, and negative 1, negative 1. In the second column is the calculation of the discriminant at the critical point. Then the Third column is the evaluations of fxx at the critical points. And in the last column is the conclusions that you may draw based on the value of d and of fxx that we calculate. For the first point, 0, 0, you have 144 times 0 squared times 0 squared minus 16, so this is a negative value. Then you can automatically conclude that the point 0, 0 is a saddle point. Now moving on to the point 1, 1, you do 144 times 1 squared times 1 squared minus 16. This should be greater than 0. Then you move on to calculating fxx, and you get to 12 times 1 squared, which is a positive number. Then you can conclude that this is a local minimum. Then we move on to the last point, -1, -1. You have 144 times -1 squared times -1 squared minus 16. This is also a positive number. Then we move on to calculating fxx, and you get 12 times -1 squared, which is a positive number. And again, you can conclude in here, you can conclude that this point, -1, -1, is also a local minimum. From this analysis, you are able to locate a saddle point and two local minimum. The next thing to do is to evaluate the output of this point. That is, you're going to substitute x value and y value back into the original functions to find the output. So for f of 0, 0, you have 0 to the 4th plus 0 to the 4th minus 4 times 0 times another 0 plus 1. This is equal to 1. So this is called the saddle point value. Now for f1, 1, you have 1 to the 4th plus 1 to the 4th minus 4 times 1 times 1 plus 1, and you're going to get -1. So this is a local minimum value. And for the last critical point, you have f of -1, -1. You get -1 to the 4th plus -1 to the 4th minus 4 times -1 times -1 plus 1, and this still gives you -1, and this is the local minimum value. So that is the last example of this lecture. In this lecture, we learned a new concept of saddle point. We learned how to identify a local minimum, local maximum for functions of two variables using the second derivative test. So that's it for me. Please let me know if you have any questions. Thank you.